So the last thing about the convergence of a measurable function and well, this Vitali theorem, the tightness and the uniform integrability. Okay, is the convergence in measure? This is just well, it's not really difficult, but it's important because sometimes you cannot control the integrals, so still you want to say that the function is going to converge in some sense. So the convergence in measure is that, well, essentially the set where the function is not converging is small. This is so the measure where it is converging is large. So actually, we're going to have several definitions. So here I choose the one in the book. So the definition. So Fn is a sequence converging to F in measure if for all eta greater than 0, okay, the limit with respect to n of the measure of the set where Fn minus F is larger than eta is equal to 0. So essentially, so this is F, and now you fix this neighborhood eta. So this is eta. And well, you measure the set where Fn is inside this interval, or where it is outside actually. So let's say now we have, this is another Fg, let's say. And now you measure this set over here. And this set is going in measure to 0. So I'm not saying that it's shrinking, it's a decreasing sequence. Just converging to 0. Indeed, as an exercise, so Fn converges to F in measure, but limit of Fn does not exist for all x. For all x does not exist the limit of F. So it's really weak.
But it exists except for some point of measure.
No.
It's not that.
No. Because you're requiring, as I said, you're not requiring that this sequence is shrinking. If it is shrinking, then it's okay. You have the opposite implications of this proposition, which is an exercise. Fn converges to F almost everywhere. And then I have to add something. I leave to you. Then Fn converges to F in measure. What I have to add here? Finite, yeah. Because I know that the set where is increasing to R, but then I'm measuring the complement, and now it's really decreasing. So you need to have one set of measure finite in order to apply the monotone, the limit theorem for measure, which is actually the monotone convergence on the measure of E less than plus infinity in E. And this is just, the proof is an exercise. You just apply the definition. So let's see an example of something which, so can you make an example of these guys? So something converging in measure but not converging almost everywhere. Actually not converging at all. Okay, I suggest it. So let's say I take something which is 1 here, and this is 1 over n to the minus n, doesn't matter. So the distance of this function from 0 well, the distance. So the set where it is larger than any eta less than 1/2 is less than 2 to the minus n. Okay? And then you translate up to 1. So let's say you have f and k, two indexes, is equal to, let's say, 1, or let's say the characteristic function of k over 2 to the minus n. So k plus 1 times 2 to the minus n. And k ranges from 0 to 2 to the n minus 1. Okay, so this is a function which is a sequence of functions because we just count. It's countable, and it converges in measure to 0. Because after some n is smaller than what I want. But it's not converging pointwise because, well, at some, for any x, well, but here, since I take the open but some points, countably many points, there is for sure an index where it is 1, no matter how large is n. At some point will be 1 again. Okay. So the important thing here is that you have something which is weaker than this guy. So up to subsequence, this is convergent. Okay, so we see now this theorem, and then we close the argument. Then there exists a subsequence, let's say f and k converging in f almost to f almost everywhere. And actually this is something that often happens, not only here. For example, well, you don't know the LP spaces, or nobody has spoken about the LP, L2 spaces. You know anything about? Little bit. Okay, so let me say that I just open a parenthesis because this is important. I mean important. It means, just underlines that this behavior is general. Whenever you are estimating distances of functions, between functions, in an integral way. So what you control is essentially some area, and you don't control the control. So you can see that Fn converges to f, let's say, in LP, if the integral of Fn minus f to the power p tends to 0. The p is the same. What you know from this is that they converge now, well, in the integral sense, so you cannot say they converge almost everywhere. And the example I had before is the same, because now the integral, no matter what is p, the distance with 2 to the minus n. Okay, so what you can prove is that Fn, there exists a subsequence converges to f almost everywhere, but not that the sequence converges almost everywhere. So to compute that, if you know that for some reason Fn is precompact in LP, to know the limit point you need, there's always a subsequence. It's strange, but it's the situation. Okay, so let's see the theorem. So, okay, I think what your classmate said is the correct thing. So I have to extract a subsequence such that the set when is larger than eta is a shrinking sequence. Well, of course, because the proof of this one is exactly that the set is shrinking. So let's build this subsequence. So idea, find subsequence such that, okay, the set where f and k minus f is larger than eta is decreasing with respect to k. This is something which is measured 0. And then it's done, because now so what it means that essentially you remove a set which is arbitrarily small, because this converges to 0, and then for the rest this is close to f up to eta. Now you repeat for a sequence of eta converging to 0, and then you have that outside, you fix a small set, outside it converges, because it's more than eta for any eta. I mean, if you it's definitely more than eta for any eta. And so essentially you come back to the almost everywhere converge. Okay, so how to construct the sequence? Okay, what you know is that you have that this measure can be as small as you want. And then you have to find something such that you are sure that all these sets are contained in that set, and the set is small. Okay? So, okay. Well, let's fix a countable sequence of eta. You need countable because then you will have to do a diagonal argument. So fix eta, let's say 2 to the minus, okay. Well, I need another index just to be sure. 2 to the minus j. And then I have this, and I know that the measure of f n minus f 2 to the minus j converges to 0 with n. So can you find a subsequence and a set such that you are sure that all these sets are contained in that set and that set has a small measure? But from here, certainly I can find n k such that this is less than 2 to the minus k. So select f n k, so this is finally such that the measure of this set is less than, okay, I say 2 to the minus k. So define okay, the set E, let's say k, I need another, the EL is the union of these sets. So, sorry, this is a mistake. So I select nk such that for every n larger than nk, this holds. Because the limit is 0, so I'm sure that for any n. So in the rest is less than nk. Okay, so now I make the union from, well, let's say from nl to plus infinity of these sets. Sorry, I said nl minus f 2 to the minus j. Okay, so what happened for this set? So for this set, sorry, I wrote something. And K. This morning from K equal to L to plus infinity. So each time I pick one of those sets. So what happened now? So first I can estimate the measure of this guy. Each guy has measured 2 to the minus k. I'm adding from k from L to plus infinity, so it's 2 to the minus L plus 1. So the measure. So let's say the measure, first of all, the measure of this set EL, and I would need another, I should put also J here, because it's fixed with J, is less than 2 to the minus L plus 1. Because I'm adding sets, whose measure is 2 to the minus L. So when I add for k, I have 2 to the minus k, but I add it from L to plus infinity. And what happened in the rest? And if, so x does not belong to this EJL, so what happened to f there? Then f, let's say, so I need to put an index here, another index, let's say m minus f is less than 2 to the minus j if m is larger than L. Okay, so sorry, this is just a mess, so let me explain again. Or unless you understand. Okay, so the thing is that first I found a sequence such that this guy for any index, so for any kf, let's say greater or equal, otherwise I have a trouble here. For any index from that onward, I have this measure is more. I fix that index, and then I found another one when it's still even smaller. And then I add all this thing here. So now I take the union of these sets, and I'm asking what happened. First I have that by choice, this is more. And then I'm asking what happened when I'm outside. Okay, if I'm outside, well, for this and L is less than 2 to the minus j and k. For another and k, I'm still outside of his bed set. So I'm sure that outside the union of this guy, for the sequence I've chosen, is less than 2 to the minus j. So I extracted a subsequence, which will be my nk, defined through this formula, and then I fix a set whose measure is small, and outside this set is smaller than 2 to the minus j. So you see, I cannot say that this sequence converges, but I'm sure that definitely it's the distance from f is smaller than 2 to the minus j. So I just remember the fact that I can translate that interval for a distance 2 to the minus j. I'm not saying it's going to 0. Okay, so what I obtain, a sequence, subsequence, let's call f and k, such that for all x, well, for almost everywhere x in E, and then I'm telling you that I did a small mistake here, but okay, it's just I apply a theorem which cannot be applied. So it's up to you to find f and k minus f is less than 2 to the minus j, definitely. No? Because the set where from, if I fix the measure. I can find the index such that this hold. And this measure is converging to 0. So it means that almost everywhere, at some point, I'm inside this set. I said larger or less larger, so this is less. Okay. Now can you conclude? Okay, so I said, okay, here the distance will be 2 to the minus, I fixed j, so 2 to the minus 1, and then I find the first sequence, and 1, and 2, and k. Then I do the same 2 to the minus 2. What happened? Doesn't matter. From this sequence, I can extract the subsequence. So this is already satisfying this guy. I repeat the construction. Well, I take something smaller. There is a subsequence, such that this guy holds, and then definitely will be less than 1/4. So I start from this. So let's say nk1, nk2, and then I do the same thing to the minus 3, and what have any sequence converging to 0. So every time I extract from the previous sequence a sequence such that the estimate hold with this guy smaller. And then, but now it's done. I take the diagonal. The diagonal is a subsequence of every of those subsequences. So I know that for the diagonal, this estimate hold for nj. So where is the mistake? It's stupid. No, it's not fundamental. Wait a minute, as I do the proof, maybe there is no mistake. Because in another proof, you have to assume that the measure is fine, but here that you see, no, no, there is no mistake. In this proof is correct. There was another proof, I remember, that was some, okay, let's go. Very well. So now just an observation, because it's very useful here. Is the following, is an exercise.
Exactly the same thing, conversion and measure with that, it's an equivalent?
It's just a subsequence.
Yeah, it's just an application or it's equivalent?
No. I mean subsequences.
Yeah, no, I mean if there is subsequence conversion to F, can we prove that it's conversion and measure?
No.
It's not correct.
I convert, no, because subsequence, then outside that subsequence you can make what you want. But even the inverse is not correct unless the measure is fine, no? So let's say Fn converges to F in measure. This is equivalent now the integral of Fn minus F divided by 1 plus Fn minus F tends to 0. Okay, and E less than plus infinity. You have always a little bit of this trick. Okay, so if you remember the exercise, well, the observation about the integral norms, and this is the same. So the estimate in E does not force you to have a pointwise convergence, but certainly you know that up to subsequence is converging. And actually from this guy, that guy can be proved directly from this fact. I think I remember because of this exercise, this maybe less of the surplus infinity. You can prove this. Okay, so that's it. And then we have done this thing, and now we start something very interesting. I mean, for me. And so far, how are things so far? Are already too much complicated, because now something is harder. Well, this is harder than what we did so far. So the title, the title is can be bombastic. So it is differentiability and the fundamental thing is AC, absolutely continuous, and BV function, and bounded variation. That in the book it is different, but I think the main point is really these two classes of functions. These are very important. So how are things so far before starting to dive into a very important subject? So these two functions, if you work in analysis, you'll find everywhere. They are I think the most important. If you work, of course, in elliptic theory or parabolic, you use different spaces. But in real analysis, this is okay, so at the end, the question was the following. The question. So, how to make this formula f of b minus f of a, the integral from a of b of f x dx, and df over dx equal to f, work in our setting. So in the sense of in almost everywhere sense. So the differentiability holds almost everywhere, and the derivative is measurable, that we know, and this guy, the integral of this guy gives me back the function. Vice versa, suppose that I have this formula for any AB, then f can be differentiated almost everywhere, and each differentiable is f. So that's the main point. And now we have immediately a trouble. We know already there is a trouble, which is the Cantor-Vitali, the Eddy staircase, whatever you call it, function. What is the Vitali function? Is a problem. Why? So if phi is the Vitali function, then phi prime is equal to 0 almost everywhere. Remember, because by construction, essentially you have this open set, the derivative is 0. And then you have this Cantor set, but the measure of this Cantor set is 0. Almost everywhere. But phi is non-constant. Okay, so there is something to be understood. It's not just that we apply what we did. Okay, let's see, however, what we can hope if this formula holds. If the formula, let's say the integral, let's say the star formula holds, then, so, because of course this seems a little bit difficult, no? I mean, how to approach this is not clear, I mean, to me. If I just look, I don't see how to do it. However, one can simplify the problem. So the integral, then write f is equal to f plus minus f minus, which are positive. And then I discover that f of, let's say, b minus f of a is equal to the integral of f plus minus the integral of f minus. So it's integral of positive functions, so these are both increasing. So this is increasing, so it's monotone increasing, and this is monotone increasing. So I discover immediately that, well, at least the class for which this theorem holds is the difference of two monotone increasing functions. Okay, so let's see if, and then vice versa, suppose that the function, so suppose now that the theorem holds for a monotone increasing function. So the monotone increasing function has a derivative and the derivative is satisfied, then okay, if any function is the difference, just use the linearity to make sense by that formula. However, I know that is not true. So let's understand for which monotone function this is true. Okay, so this will be the line. So after this observation, we study monotone functions. We see if they are differentiable, if the fact that this differential almost everywhere is just a case or is the general, and what is going on in general. Okay, that's clear. This is just the abstract of the theory. Monotone functions. So what is the definition? In R there are several definitions, so let's see, give me one, and then maybe I find another. F, pardon?
X is less than F implies that the image of F is less than or to the image.
There's another about the level set. The level set, the upper level set are just half line. I think it was an exercise. Okay, this is perfectly fine. So first, so we do, instead of the theorem, we do some observation. We do the theorem as observation. So the first question, what?
This is increasing, not just more.
Is this?
I mean, this is increasing, monotone.
Yeah. We do just one for one, increase. There are some automatic assumptions, no matter what. So it's always a monotone will be increasing. And then, okay, if you specify, it's decreasing. And it's like the entropy for mathematician is convex. For physicists, it's concave, but whenever we have a function which has a double derivative with a sign, it's convex. It's not concave. Well, unless you specify, it's concave. Okay, so how many? Well, okay, let's see. First observation. I just state and then you say you believe, you don't believe. There exists f the limit for x which converges to y from the right of f, and the limit from x which decreases to y, the right and left limit of f for any y. True or false? True. So how many believe it is false? How many believe it is true? Why?
It's wrong. It's wrong.
This guy?
No.
Well, it could be wrong, because maybe I just tried something and then I did something different. There is still a possibility. But the thing is, so, and why?
Because for a monotone function, if the limit from the left not exist, means it goes to infinity. So when we go to the right, we cannot start and
Because being a monotone is a liquid of the sequence.
what?
Being a monotone, you can only go in one direction.
Yeah.
Yeah. So,
So if
like
it-
the supremum or the infimum.
Yeah.
Like, so because the limit for x to y is equal to the sup f of x.
Less
And
than
this-
f1.
Hmm?
It's less than f1.
This depends on what you say about the limit. Yes, it depends if you want, I think, the limit without. So the limit of this guy for x, which they do not assume the value y. Yeah, because there's a sequence which is less than y converges into y. It's not y. Y is not allowed. It's a sequence. That's okay, no? So this is, and the other is the infinite. Okay, so we have that there exists at least the right and left limit. When they coincide, it's continuous. Is it true or not? Let's say the limit. So let's call this guy f of y from the left, and this is f of y from the right. If f y from the left is equal to f y plus, then f is continuous. But he's right. As I said, that these are not just my choice, that the limit in this notation means that I'm not taking the value y.
That is correct.
It's true?
Yeah.
Why?
Because if they are equal, then value is at that point. If we suppose it's not equal to the limit, then it
Yeah.
cannot
So
be-
it's forced by this inequality, no? Should be less than the value on the right and the left. Yes. Okay, so the question is how many, so let's call, so how would you call the points where you have, and which inequality can you have here? Equality or which one? Which would be the larger? The larger. The bigger, yeah. This guy, no? So either equality or this guy. So what the guy which satisfies this guy, how would call the points for that the limit from the left is strictly less than the limit from the right.
Discontinuous point.
Discontinuous point. But usually, for some strange reason, I would call it jump point. And jump is really for this kind of monotone, for BV functions. It's the notation for BV functions. How many?
Cantos.
Hmm?
Like most cantos.
As most, why?
What? What do you-
Canto.
Ah, yeah.
Yes. Why?
Because of the density of Q in R.
It's even easier.
No, because if it's not if we take this is notation, but I believe it. If we take the sum of strictly positive numbers over something which is non-countable, it is infinity.
Yeah, of course, yes. That's the,
Yeah.
how to say, the measure, not the measure, the separated way to state it. Otherwise, you will do the proof. How many can you have larger than epsilon? So how many jumps I can have larger than epsilon? Because the number of points y such that fy plus minus fy minus is larger than epsilon is less than. Okay, it's very easy to think. So this is a monotone function from here to there. How many steps I can have? If the height is 1 meter and the size of one is 10 centimeters.
Fg minus Fa over.
Yes. Now we'll take account of sequence of epsilon, and then so it's finite. So the union of counted many finite sets is counted. Okay, so we arrived at this.
And what is A and what is B?
Is an interval. Sorry, yes. So F is monotone in A, B. So this is, let's say, a remark. Or F is equal to, is extended to, let's say, A. So F of A for X less or equal than A, or F of B X larger or equal than B. So any definition you want. So I'm saying you can extend it. It can be also plus infinity. In that case, okay, it's a monotone in the open set. But so the monotonicity in open sets, well, the import is just technical. I prefer not to enter into it because you understand exactly what is going on here. Then you will make this precise. Well, this is precise. So another question: can we make let C contained in 0, 1 countable? So let's take it open to be short. Countable. There exists F monotone such that the jump point, which is defined, so that the jump point of F is equal to C. Statement. True or false?
Just a remark about just what we stated before.
Mm-hmm.
We said that the set where there is no F is not continuous is countable. But I believe that even it cannot be dense, something dense, no? So if it's something dense like Q or something, we cannot.
Okay.
Yeah,
Is the exercise here?
yeah, that's why.
So you're saying
Something
this is false?
dense. Yeah, if it's something dense, we can.
I'm saying it is true.
But
I'm saying it is true.
for every countable, even if it's dense. It's hard to see.
Why? But yeah, for the first time it's hard. So let's do the following. I want to have a jump here. Can you give me the simplest monotone function who has a jump in that point?
The characteristic function of
Now I will have another jump here. Can you give me another? So I have the previous one, then I want to have another one. What do you do?
we add the characteristic function of
Yeah, but then after you do too many functions, this is going to blow up. I don't want that this to blow up.
That's why you take them out.
1.5. Something here. So let's make 1/3, just because we will see.
1 over 2 squared.
Or 2 to the minus n. Yes, that's okay. So I make a jump smaller in order not to arrive. Or I just add. I just add characteristic function, no? Such that the sum of the height is bounded by 1. This function has a jump in each of the set of the point of C. Take any point C. Then there is a function who has a jump. And the inequality tells you that you are not going to cancel that jump, because you are just adding monotone functions. So this guy is the sum of the the difference, this guy minus this guy, is the sum of the differences. So the solution, yes. So f is equal to the sum over n of the 2 to the minus n, the characteristic function of the point Cn plus infinity. Well, now we can choose if we close or we don't close, it's just the value in the point. So it can be very bad. Question. Is a function like this one going to satisfy what I cancelled, the theorem fb minus fa equal to the integral of f, and f is equal to f prime? No, there is no. Because one observation is that clearly if f satisfies this guy, f is continuous. Why? It was an exercise, I think. Because when the set converges to 0, which is so f of x plus h minus f of x, x plus h, and when h goes to 0, for a function which are integrable by definition, they converge to 0. Okay, so it's done, cannot be discontinuous, but it's still monotone. And now, this is something big. So we keep the monotone. These are just elementary stuff. And the code is okay. Definition. Vitali covering. And then people who are not Italian, they call it a fine covering. But since we are in Italy, it's a Vitali covering, of course. So let I be a collection. Okay, the notation is indeed it's F. Be a collection of closed intervals. And comments later. So F cover E in the sense of italic. If for all x in E, for all, let's say, epsilon, there exists an interval in the collection such that, okay, what I mean is that x belongs to the interval and the interval, okay, has length less than, yes, the length, I wrote it this way, the length of the interval is less than epsilon. Okay, the version which is written here is not the best in order to write for general, in the multidimensional case, whatever, but it's fine. So some comments. So there is one point which is usually, this is what happened to me, usually you forget about it, or you really don't put attention, but actually it's very important. So let's see the thing. The thing is that so I have this strange set. I'm not requiring it to be measurable, because the definition is this. I take any point, I take a neighborhood, which is essentially this epsilon here. And then there exists an interval which contains the point and is inside the neighborhood. And what I did not say something here that is written there. Close. So the theorem works for closed intervals. Usually you manage also for other types of intervals. There are a lot of results using other types of coverings, but here it's very important to be closed. And then only you adapt. So let's see what I can prove now. Lemma. Let E such that be such that the outer measure not requiring to be measurable less than plus infinity, and F cover E in the sense of Italian. Then, for all epsilon, there exist finitely many intervals in the collection. Because then something, and they are disjoint, such that the outer measure of I think this is the symmetric difference. It's written, but let's see. However, is E minus the union of these intervals is less than epsilon. But I'm pretty sure that what you get here is the symmetric difference. Well, let's see. Actually, I'm sure you get the symmetric difference. That we are. Okay, so let's do the proof. And the proof has one clever point, very clever.
Probably we can say that E can be written as the union of a bounded set, a compact set, and something else of measure less or equal than epsilon. And
Yeah, then okay, then.
And then
Well,
we
wait
can
a
go
minute.
to the
No,
boundary.
wait a minute. This is not measurable.
What?
Not measurable.
Yeah, yeah. So we can do that. I'm talking about outer measure, of course, not the measure.
For the outer measure, you know that you have an open set.
What?
From outside. You just can approximate from outside if it is not measurable, not from inside. Otherwise, it's measurable. So the Vitali, the non-measurable set, every compact set inside that non-measurable set is measure zero.
Yeah. No. I said that the set E,
Mm-hmm.
we can write it as something compact, union, something else, which has measure less or equal than
No.
epsilon. Why?
Otherwise, it's measurable. So you know that E is the infimum of the measure of open sets. So you can write certainly there is an open set whose measure is almost E.
Yeah.
Well, this cannot be said, the outer measure. And then, but you cannot say that this is equal to the supremum because otherwise it's measurable.
Yeah, but I was talking, when I said that E is written as two sets, I said that the outer measure of the other, of one of the two sets is less or equal to the epsilon, no? I am not assuming that one of the sets is measurable.
I'm not so sure. For the non-measurable sets, you can for the example we have, every subset of that object has probably, well, that's not true, but almost. I don't know. I don't see how you divide. Well, you can divide it into pieces, but then it's still. I don't see. I don't understand. So you cannot put a measurable set inside whose measure is almost the like of the one of E. So you cannot put a compact set with measure is E. You can put other non-measurable sets, but. Okay, so let's do the proof. I will do the proof in a wrong way and then ask you how to fix it. Okay, so I take, and then this is the sketch, which is wrong. Okay, so I take the largest. Let's do this then. I prefer to work here, and we have some fun. I will leave some space, and then we fix the step. So each step. Okay. So essentially, what I have to find is a sequence of interval which covers everything, but not too much, because otherwise. Okay, then fix.
A question. Does this kind of cover always exist?
The cover of F?
Yes.
The F is a cover which is, so you for example have some property of every point. And the property is that, well, typically, if you do the limit of a functional in that point, you get a value. So you know that if you are sufficiently close, or for subsequences even. So you know that for any, there is a subsequence converging to that point such that the values of the function in that interval is the one you want. So this gives you a fine covering. Can you deduce from this pointwise property a global property? And we will apply as follows. So just to see how. So for example, we apply to assume that for each x, the lim sup of x plus h minus f of x divided by h is greater or equal than 0. And f is continuous. This is an exercise. Then f is increasing. This is a typical application. Because this property tells you something pointless. For any point x, the lim sup, so the lim sup of the derivative, the upper derivative, is positive. I'm not saying C1, the derivative is positive. I'm not saying that the derivative exists. Just say, well, the lim sup can be plus infinity, but I have 4 subsequences. So this tells you that for any x, well, there exists a sequence of hi converging to 0 such that this guy is greater or equal than 0. And so this gives you a covering. For any x, you take the interval such that this limit, this quantity is, well, in this case, is greater than minus epsilon, with epsilon fixed. And then how to deduce that a global property, so it is increasing globally. So this is an example that gives you immediately a covering which is not the balls or the intervals. The intervals is a fine covering. The topology is a fine covering for sure. Indeed, this is a subfamily of the topology. But actually, so the application of the lemma is really that from a local thing you deduce something global, because okay, here you have to use the continuity. Okay, so let's do the proof and fix and so on. Fix I1 is equal to the max of the length. Okay, step 0. Fix O, which contains E open and the measure of O minus the measure of E is less than whatever I want. So I have an epsilon there, so let's put epsilon half here. This is how to obtain the part which is not great. So now take, because the construction, so the proof, to prove the theorem, you have to give me which intervals you choose. So whether to prove the interval exists, because, okay, you have a region, or, or you give me a method. Okay, I give you a method. Take I1, the first interval to be the max, the sup of the length of I in F and I contained in O.
That's a real number.
Sorry, yes, the argument. So the I which maximizes. Okay, so here I look to all the I can choose, and I take the largest. So what is the next? Which will be the next? So basically I choose the longest one. And then I'm looking around, so I just move on the other part. And the situation is the same, because the open set minus this I1 is still open. So what I do, if I1 IK minus 1 is given, I choose IK is equal to the R sup, the length of I is in the family, I is contained in O minus the union up to K minus 1 of I. And then I'm fine. You see why it's open. So I can repeat the procedure. Then this is and now what I have to prove is that essentially, well, first this sequence is converging, and then if I can fix n such that the rest has a measure very small. Are you following? I know the proof. This is probably one of the most difficult proofs we have in. Not because it seems easy, but it's a deep proof. Okay. So is it true that the sequence, the sum of this length is finite? So the sum of the length of, so I proceed up to 5. If I finish, it's done, no? Otherwise, what is the sum?
The length of the union.
It is the O, and most can be O. Everything is inside O, and they are disjoint. These are clearly disjoint, so. Okay. And now I'm asking, what is the measure of what is left out? So the question is for if the measure of what is out is finite or not. So it's small. Because, okay, I can proceed. I'm not saying that the union of these guys is equal to the measure. I mean, a priori, I don't know. Let's see, how do I do that? Just to be sure I'm not. Okay. So I want to measure, so the outer measure of minus the union up to some n I. Right, so let's see. Here I choose another one, here I choose another one, another one. So let's say this point x. This point has not been chosen. So it means that I never choose one of the intervals which contains that point for the step I to 1 to n. So I'm saying why I've not chosen that point. I go back here. Well, it means that at any step, the interval which contains that point has a length which is less than the supremum. Because you see, let's say I arrive at the step n. I have to choose the step n plus 1, and I have that point outside. So I look at all the family of intervals I have, also the intervals which contains that point. And then I choose another one. Okay, it means that the length of that interval cannot be larger than the length of the others. Okay? Because otherwise I would have chosen. So it means that if x bar has not been chosen at step n. Okay. But what does it mean that I'm not so well, because I'm trying to change okay. Then the interval I bar containing x bar. So either is not the maximum, or it intersects another one. It is not. Oh, sorry, it was not the max for I equal to 1 to some n bar, and then it intersects from n bar. Sorry, because I try to decompose the proof, because otherwise I just go straight. Okay, let's do the reasoning here. So this x bar is one of the intervals I bar in the covering by assumption. So I'm asking why I'm not choosing that I bar. Because my thing is that x bar is not inside this union. Why I have not chosen it? Two cases can happen. The first is that, well, it was not the master supremum. I'm always choosing another one. Or it's not here. It intersects. Okay, but when it is intersect, so the first index for which intersect, its length cannot be larger than this. Okay? So, the length of I bar is less or equal than the length of I n bar. And we will repeat again. I'm sorry, the proof is. Do you agree? This is the important observation. So why the point x bar is not being chosen? Well, there are two cases. Well, it means that any intervals of containing x bar has not been chosen in my sequence. Then I look how I build the sequence. Well, I'm not choosing that interval either because it's not the supremum, But once its length becomes larger than the length of ik, and since it is converging for sure at some point is larger, then I look at the condition is this one. It is intersect the previous one. And so it intersects exactly any interval whose length is larger, because otherwise I would have chosen. So I'm not choosing I until the length, I bar until the length is small. And then this can be separated. When the next one has a length smaller than I bar, cannot belong to this family. So it intersects from one to the previous one. Which means essentially that this length is bounded by the length of the last one I choose before the intersection. Okay? And now, so at some point these intersect one of these I, let's say n bar. And now I say, oh, look, if I enlarge this I bar by 3 times, is true or not that I bar is contained? So then I deduce from this observation that I bar is contained in 3 times I n bar. This notation is not precise. I should say I fix the center point of R, I n, and enlarge both sides. Okay? So now what is the measure of the left or the rest? So for any at any n, okay, can you conclude now from this observation? This proof is full of gaps. But then to fix the gaps is just a technique, but to understand the proof is not. So let me make the last point, and then we repeat again. Point 5, then P minus the union up to plus infinity of my sequence is contained for all L in the union from L to plus infinity of 3 times ik. For any point, if I say that I'm not taking L, I can enlarge what is left, and for sure it is one of those. So the measure of minus the union is less or equal than the sum 3 times the length of ik, and this goes to 0. So I can fix a finite number such that is less than epsilon, and these are disjoint, and that's that. Okay, let me repeat again. The proof has some gaps, but let's assume I can do all the statements, and then maybe now I comment. So the first thing is that, okay, this is the trivial thing, I don't need it. Something to be bounded as small. I don't want to have a covering which goes too far away from my set. So I have to give you a method to construct the sequence. And of course, I take the largest one. This is the natural one. So let's start to remove the largest part and then see what is left. But clearly, I cannot say there exists a supremum. So the correct is that at least so the length of IR is larger than 1/2 the supremum. For sure, this I can do that. And then I take the next one with all the intervals which are not inside this guy. So the length 1/2 of what is they are disjoint, and then from the point 1, I'm sure that they converge. So what I need just to prove is that if I remove the first, what is left is certainly something which goes to 0. Okay, let's look at what is left. So, let's look at this set. So this set, I take a point outside, and then I say, okay, by defined covering, there exists an interval I bar, which is not inside here, and it contains X bar. I never choose that interval. So what happened for this interval? Well, since I never choose that interval, it means that when its length was smaller, of course I don't choose that interval because it was smaller than 1/2. At some point, it was an interval I could choose, but what happened is that cannot be inside this guy. And now we change the constant. So the length is 2 here, because I put 1/2. And now how much I have to enlarge it? Question. This is the interval, and then so this is the interval, and it intersects an interval whose length is larger than 1/2. How much I should increase the small interval in order to cover this guy?
3 times 3.
Yeah, I put 3, sorry. So that it's a 5 times. 3 from one side, 3 from... So actually it should be... Yeah, I increase it linearly 3 times, but actually I need 5 of these intervals. No? When I wrote 3 before, was... sorry, because I thought something like this. So the length is 3 times. And now I need 5 times. Because this is 2, 1, and then it could be on the other side, 2, 2. 2. So here it becomes, okay, I enlarge by 3 times, and the total length would be 5. So let me write 5 magnitude. So when I go back, here I obtain 5, and here I obtain 5. Now it's correct. This is difficult to digest, but actually the method is this one. Questions here? Okay, then we have the derivatives. We will do it next week. Want me to do again graphically the proof? Once more time, graphically.
I mean, in the proof, we didn't use the fact that, I mean, one of the characteristics of Vitali's covering is that at each point, I mean, you can find an interval, I mean, of length at that point.
When I say that x has not been taken up to that one, I take an interval which is not in the first union, and I say y is not covering, is not covered in the next sequence. Well, because at some point it intersects one of the following intervals, and so it is contained in the union of the rest and larger by 5. I use in that point. Because otherwise here I should add from 0. Instead I can add from L, in this case from N. And when you try to do the proof not in a direct way, but to construct, you always forget some pieces. The question was very good, yes. I did not put attention on it because my attention was in the procedure, and that is the basic observation also. And, this works, the same proof works also in any dimension. You replace intervals by balls, closure balls. Then if you are careful, you observe that, well, I don't really need intervals. So what I need is something that when I enlarge it, I can cover nearby sets. And so there are, so this is in the general case, there are statements which tells you what is the structure of the set. Okay, so I think we stop here. Please try to digest the proof.